So let's get started. So today we're talking about new functions from old. And so to start with, we'll do the easy stuff. And what I mean by easy stuff is, here it is, definition. Given f from a to the reals and g from b to the reals, where a and b are subsets of the reals, we define now there's one. It's like some sort of conspiracy of this side of the room, like all being gone today. Like, I don't know what's going on here. It's very, they're asleep. I mean, I wish I could be asleep right now. That'd be amazing. You did nothing stopping me? And let you guys go? It's very kind. It's very, very kind of you. Let's see here. So, f plus g of x is equal to f of x plus g of x, 2 f minus g of x is equal to f of x minus g of x, 3 f times g of x is equal to f of x, g of x. So just to let you know, we have names for these. So this is the sum. I mean, not use this marker's not quite alive. So so this is the sum, difference, and product of f and g. So the sum, the difference, and the product of f and g are defined as follows. So in particular, the sum is f plus g, the difference is f minus g, and the product is fg. These are new functions, and these definitions I've just made these are called point-wise definitions because we define them one point at a time. And then the question is, what's the domain of these new functions, right? See, because the set, like A is the domain of f, B is the domain of g, right? See, domain of f is A, the domain of g is B by assumption, right? Can you tell me, like, what's the fine print here? What's the terms and conditions? That's for all x what? For all x in A intersect B. So the domain of the sum, the difference, the product function, it's the intersection of the domains of the functions which are being combined, right? Because in order for those formulas to make sense, we need both f of x and g of x both to make sense, right? Which is to say that we need the point to be in both of the domains of the respective functions. So, let me shut my door. That phone is always ringing, and it's never anything interesting. Now, what else can we do with two functions? we could do what? We could divide them, right? So that's case 4, which is also called the quotient of f and g. So f over g of x is equal to f of x over g of x. And this is for all x in the intersection such that what? There's an extra condition we need here for this formula to make sense, which is what? We've got division in this formula. What do we need for the division to make sense? We need, there's an extra string attached here. We need g of x to be what? To be non-zero, right? So for all x in the intersection such that g of x is not equal to 0. So that's how we define the sum, the difference, product and the quotient of two functions. Now let me just, let's look at an example, right? And I think the main kind of tricky thing, I think, for you guys probably is just figuring out the domain of the new function, right? Because that's the part, I mean, everybody can do these operations, right? Like adding, subtracting, multiplying, that's not a big deal. So the domain is a little bit tricky, though. So let's look at an example. We could have, say, f of x equal to the square root of 2x minus 1. And we could have g of x equal to the square root of 3 minus x, right? Is it possible that, like, you can't add two functions?
Yeah.
What would that take? When would that happen? Like, when would it not even make sense to add two functions? When the domains don't what? Like, yeah, they don't overlap at all, right? If there's no x, which is common to both domains, like if the intersection of the two domains is empty, then there's, kind of not anything to say there. Like, you can't combine the formulas if they've got no common ground, right? So what's the domain of f? What do we need? So what happens if we have square root of a negative number? We're in trouble, right? We can have 0, it can be positive, but we need that 2x minus 1 is greater than or equal to 0, right? So we need 2x minus 1 greater than or equal to 0. And so that's 2x greater than or equal to 1, which is x greater than or equal to 1/2, right? And this one, we need 3 minus x greater than or equal to 0, which gives me 3 greater than or equal to x, right? Or you could also rewrite that as x less than or equal to 3, right? So if we draw a number line to organize our thinking, and I strongly advise that, right? If you're trying to figure out, if you think about intersections of sets, number line's a really great tool to do it. So we've got 1/2, right? And we've got 3. So x being less than 3 means what? It's to the left of 3, right? So I'll use red for that. So that's like this, right? And x being greater than 1/2 means what? It's to the right. I will use whatever color this is. What is this? It's not exactly purple. It's like burgundy. You might be right. Let's see here. It's like that, right? So where do we have both? It's between 1/2 and 3, right? So in this case, what I'm arguing is that my A intersect B is just equal to 1/2 to 3. In this case, they're both included because we don't have division by 0, right? Those at 1/2 and at 3, we have either one or the other. The functions is 0 as it happens here. So, okay, great. What's the, okay, so the formulas. What are the formulas? F plus g of x is what? What's f minus g of x? What's f times g of x? What are those equal to? I mean, it's just this, right? You just add the formulas or subtract the formulas or multiply them. Now, I will say the multiplication I could simplify a little bit. Can simplify product in this case. I don't necessarily expect that you simplify the formula for the product. I'm just pointing out you can do it. If I wanted you to simplify it in a given problem, I'd tell you. So what can we do? If we got the square root of 2x minus 1 times the square root of 3 minus x, what can we do? Did you know this algebra? Square root of a, square root of b is what? Square root of ab, right? So if we make that simplification, in this case, we get square root of what? 2x minus 1 times 3 minus x. And of course, you can multiply it out, but like there's a slightly simplified formula for the product. Now, one thing I will warn you about here is when you make a simplification of the formula, like when you use one of these definitions and you make a simplification of the formula, it's possible to change the formula into x. Like if you were to ask the question, okay, well, what's the domain? If I just gave you another function, right? And if I just gave you the function h of x equal to the square root of 2x minus 1 times 3 minus x, right? I said, okay, here's a new function h, and here's its formula. What's the domain of h? You're like, well, isn't the domain of h just what you just found already? Isn't the domain of h just like 1/2 to 3? I mean, that's certainly the domain of the sum, the difference, and the product functions, right? But something kind of sneaky happens. When you combine these two, you get a single input to the square root, right? And if you think about it, the original one basically assumed plus plus for both of the roots, right? But once you're just looking at this, you could also have minus minus, right? And it could be, in principle, that you add new points to that. I don't think that's actually the case here because I think when these are both negative, like there's nothing to add. If 2x, I think this actually, the subtlety I'm talking about here doesn't happen for us because essentially the other case I'm worrying about, like when they're both negative, corresponds to like reversing the red and the purple and the burgundy arrows. And if you think about that, there's no x which are both, if I draw it. The other case that I'm worried about would be like this, the red one would look like that, and the burgundy one would look like this. And if you think about it, like logically, there's no x which simultaneously makes both of these negative. So it actually, despite the fact I simplified it, still has the same domain as the original unsimplified formula. All right, I'll stop talking about that. I just would warn you that when we make simplifications of formulas, we can change the domain of the expression in kind of subtle ways. All right. Another example. Oh, I guess there's one other thing I should do with my example. Example 1, what's the promise it's not the COVID. Let's see here. Sure. Say sure. Let's see here. Where was I? I'm pretty sure I had it like back in February anyway. I went to Disney World right when this whole thing started, and my son and I both had like this mysterious sickness which kind of came and went and hit us pretty hard. It was like a flu, but it was worse. I'm pretty sure it was that. But anyway, how about this? The one thing we haven't done with my example 1 is what? What's the other function we can construct? We can look at the quotient, right? So let's do that. If we have f of x, f over g of x, that's equal to what? That's equal to f of x, which was square root of 2x minus 1, divided by the square root of 3 minus x, right? And hey, you know what? While we're at it, we could also do g over f, couldn't we? What would g over f of x, what would the formula for that one be? Same thing, but flipped over, right? Like that. And what would the domain for f over g be? It's the domain. So let me put down the numbers. 1/2 and 3. Right? It's going to be basically the intersection of a and b, and we got to throw out points what? Got to throw out 3. Why do we have to throw out 3? 0 on the bottom. Perfect. And how about the other one? What's the domain of g over f? Switch them, right? So 1/2 has to be excluded because that's what makes that 0. And the 3 gets included because it's harmless. It just makes the numerator 0. In contrast, of course, the domain for all 3 of the sum, the difference in the product functions was just 1/2 the 3, where both of them are included. Okay. So pretty much all I have to say about that. In terms of like the formula, there's 2 other things we can think about. The one thing we can think about is, suppose we're not given a formula, right? Maybe we're just given a table of values. Maybe we're just told something like, suppose f of 2 equals to 3 and g of 2 equals to 7, then what can you do? You can calculate f plus g, right? F plus g of 2 is what? F of 2 plus g of 2, which is 3 plus 7, right? So you get 10. Or you can calculate f times g of 2. What would that give you? F of 2 times g of 2, which would be 3 times 7, which would be 21. So notice that you can calculate the value of the sum of 2 functions or the product of 2 functions at a point, even if you don't have formulas for them, right? If you know the value of the function and the other function, then you can figure out the value of their sum or their difference or their product or their quotient, right? Like what's f over g of 2 equal to? Apparently 3/7, right? Great. I think what's more interesting, though, is that if you have the graph of 2 functions, like the graph of f and the graph of g, you can create like the sum or the difference of those 2 functions. And I suppose in principle you could create the product of the functions as well, but I've never taught that because, whoa, I don't want to try to figure that out like on the board. It's never a question I've ever asked either in like a test. I mean, I guess in principle you could multiply two functions graphically, but I don't see people do that. So now, here let's look at a graph, and suppose we're given the graph. Let's see here. So suppose I'll make this one a little bit more interesting. Suppose here's y, here's x, and let's let this function kind of be piecewise defined, right? So in the sense that f of x is given like as follows. Like that, all right? And then suppose that's y equals f of x. All right, and I'll put some numbers in here just for the sake of discussion. Let's suppose that this over here is minus 4, and the break point over here is at 4, and I guess this will be over at 7. All right, so there's y equals f of x. And then let me give you the graph of y equals g of x. So let's see here. Well, I'll let it, I won't break it, I'll just let it go like this. There we go, y equals g of x. And so g is going from minus 3 not included all the way over here to this point, which we'll say is at 6. So what would the domain of f plus g be to start with? So we need to look at the intersection of the two domains, right? So in this case, the domain of f goes where? It goes all the way from like minus 4 not included all the way to 7 not included, right? Everything in between that has got a value, right? In contrast, the blue graph, it goes from minus 3 all the way over to 6, right? So when you take the intersection of those two domains, what happens is that it just becomes the domain of g, because g is a subset of the domain of f. So like the domain of the intersection is just basically it's the x values for the blue graph is all it is. So it goes from minus 3 not included, not included, over here to 6 included. These are the x's for which we have values for both f of x and g of x. All right? Now let's add these functions. How do you add functions? So again, just the instructions here are example 3. It's like construct f plus g graphically. That's what we're doing, okay? So unlike my first example, we don't have formulas, right? Instead, we were given graphs. Right? So I'm gonna make the sum function in red, all right? And let me just start out right here. So at minus 3, we add f, what's that do? See f down here? F is negative, right? So adding the value of f actually brings us down that much. So like we start out about right there. Although I should probably draw an open. Right? And think about this. If one of the graphs is 0, right, and we add 0 to the other graph, what happens to the value? It's just equal to the one which is not 0, right? So if you think about adding the brown to the blue, then when we cross the x-axis right here, we're going to intersect right there like that. So, and this, so it kind of goes like this. And then now over here, the brown graph is positive, right? So we're going to start adding. Like, basically just take whatever this distance is, like that, and think about scooching that up there like so. And let's see here, this one. So basically I think about taking this and then moving it down like that. So let me just go ahead and draw it actually.
Where did you get the first one?
This one, so I have to go down this much to get to the brown line. So at the same, I go up here, down here. Like we could put some numbers in if that would be helpful. Listen, let me erase some of my arrows and just draw the graph in. I think that's probably the most productive thing I can do at the moment, because it does get awful busy if you try to draw your thought process as well as the graph. Let's see here. So some things I use that are helpful is that when the one graph is 0, we're at the other graph. So like I already know that there's some places where the blue graph is 0, right? And there's some places where the brown graph is 0. So like, oh, goodness gracious. So we should go through that point right there. And let's see here. We'll drop down when we get here. That point right there. We also have to go through essentially that point. My dotted lines are kind of crooked, I'm sorry. I'm trying. Let's see here. When we should go through 0 when these are equal but opposite. So if this distance and that distance are the same, so it's somewhere there's a crossing somewhere in here where the brown is as much above as the blue is below. So I mean, I'm guesstimating it's somewhere in like right about there. And again, it has to come over to here. There should be a jump, right? Oh yeah, I don't have to. Should I connect like that? I should not. The thing is, there's a jump. So what I should be doing is this will, let's see here. This does something like, something like that. And then it jumps at that point. When I add the blue, let's see here. Oh, but that's filled in. Let's see here. I think it jumps, this plus that actually is down here lower still. I think it jumps down to there, roughly speaking. Then it should go up to here. And then it should, good grief. I can't draw this, hardly. If I was smarter, I would have made something easier to draw. But by now, you know I'm not that smart. Let's see here, so. Curses. Well, I tried. I think this example is too complicated. Let's try something easier. I mean, the idea of the example is fine. It's just this one I will make very, very simple. I will make, let's see here, I'll go from -5 to 5. And I'll just let y equals f of x equals to 3. All right? And I will make g of x be something relatively simple, like try for at least some kind of jump here. Then I'll let that be just constant like that. That should be easier to follow. I'm going to let them jump here at 2. All right? And let me add some more points. Let me say that that point is -5, 1. This point here is 2, the hole in the graph is 2, -1. This guy up here is 2, 1. And I said f of x equals to 3, but clearly from my graph I should have said f of x equals to what? If this is 1, what is the other thing? Is 3 reasonable? Probably not, right? What should it be? You guys tell me. If this is 1 up to here, then that should also be, it should be at 2, right? F of x equals to 2, given the scale I've set. All right, so to add the graphs, it's very simple. All you do is take the value for each one and add it, all right? So let me actually explicitly do that. What's the black point here? That one is what? That's -5, 2, right? So we add the y values and we get to what? 1 plus 2 is 3, right? So it's up here. And when we get to 0 right here, we'll get to that point. So basically, if you add the blue to the red, if you add the blue to the black, you're like up here, like that, right? When the blue crosses 0, the red line crosses the black because you're adding 0 to it. And this continues, right? Let's see here. What is -1? Excuse me. What is -1 plus 2 is what? It's at 1, right? So basically, this is going to go down to there. Why did I add -1 to 2? So right here, this, and I should fill in one of these holes. Which one do you want to fill in? The top or the bottom? All right. So, okay, so to figure out the value of the sum function, I have to add -1 to 2. Because up here, we've got 2, 2, right? So like f plus g of 2 is f of 2 plus g of 2, which for my example is, I never told you that the blue one was g, did I? But I should have. So g of 2 is what? G of 2 is -1. And f of 2 is 2, right? So we have 2 minus 1, which is 1. So I'm drawing the sum function in red. So basically I have to fill in the dot here for the red one. And then what happens? Then past that point, we add the blue and the black, and where do we go? 2 plus 1 is what? is 3, right? So it jumps up here like that. If you feel lost right now, do not feel bad. What I'm describing is actually not that complicated. It's just really, really hard to follow somebody doing it. If you just do it yourself, in this particular case, more than anything else, it will be better. Yeah, I think you'll be less confused if you just try a homework problem. Hey, how about this? Problem, let me tell you. I mean, I have recommended homework that's on this, yeah? So, the homework problems I'm suggesting you could do that would be helpful would be like number 21 on page 216. So, number 21 on page 216, see, it actually gives you like a curve and a line, and you're just supposed to add them. But this is an odd number, so you can try it yourself and then look at the odd number in the back and see if you understand or not. But all you do to add functions graphs is just add the y values for the x values which match up. Now this is physically interesting because, any of you guys have like noise canceling headphones?
Yes.
These actually work on this principle. So if you think about f and g both being, say, like the intensity of sound, right? Then as a function of time, if you could add, if you have one wave that looks like this, right? If your one wave is like this, if that's your f, and then your g looks the same, but flipped over like this, right? So if this is y equals to g, and this is y equals to f, and I'll say t because usually we think of t as being time. These are, intensity of sound in time, something like that. What happens when you add these two? They just cancel out, right? This is called destructive interference, but that's, if you think about it, just adding graphs. So, the way the headphones work, I think, is they take the input sound, like the blue from from the ambient environment, and they create the anti-noise to it, the red, and feed it to your ear. So what you hear is less, right? Of course, no headphone can do it perfectly, so it's just kind of like this is the game, but it's never completely perfectly executed, right? If you've worn these headphones on a plane, can you still hear the engines? Yeah, despite the advertising, right? I don't know. I don't have a pair personally, but I'd like to have one. Okay. Anyway, enough about that. So again, I'm sorry if I've confused you. If you look at the video I posted for the other section yesterday, I actually do something on paper with adding, and I do think like my work on paper for this particular topic works out better. It's just, anyway. All I'm trying to say is I think it is much easier to do the homework problem here than to follow the in-class example. All right, so next up, we have I would say, much more challenging topic. And in the sense of, you can add, subtract, multiply functions to your heart's content. It's not probably going to be a problem for you. These graphical examples, once you figure out what's going on, they're actually not bad. But the composition of functions, this is a topic which requires practice. So here's the definition. Let f and g be functions on the reals, then f composed with g of x is equal to f of g of x. This is what your book says. Now, your book is oddly silent about what the domain of the composite is, right? What would you need if you think about this? Like, what would the domain of the composite function be then? Right? Like our general rule is the domain is the set of x for which the formula makes sense. So if you think about it, this is going to be true for what? For each x in the what? In the domain of which function does x go into? Yeah, into domain of g, such that what? Such that g of x is, see, g of x is the input into f, right? Such that g of x is an element of the domain of f. So what I'm trying to tell you is the domain of a composite function, it's kind of a little bit trickier than those ones we just did. It's not just the intersection. It's something kind of tricky. And so your book has a low opinion of you, and it doesn't tell you this because it thinks it'll confuse you. I have a higher opinion, so I told you. But your predominant responsibility in here, your main responsibility is just to learn how to actually find the formula for composite functions, all right? So let's do a bunch of those and try to get good at it, all right? So I'm not actually, that's as much as I'm going to say about the domain of a composite. I'm not going to talk about it anymore. We're just going to find the formula, all right? So, was it? So a little bit of language I should mention, because this language we keep using in calculus. Here, g is the inside function. And f is the what? The outside function. Right? It matters, right? Which one's in and which one's out. What do? Do you put your shoes on first and then put on your socks? Or do you? Yes? Says the person with no socks. Nicely played. What? It was a valid joke. I'm being shamed. Just with the eyes, but still, I feel shamed. My joke has not been accepted. Now she's doubling down on the scorn. I like it. It's good. We should all be, more of a troll in real life as opposed to just online, don't you think? The world would be better that way. I'm joking. Don't be trolls. Anyway, so let's see. Let's look at two functions. F of x equal to 2x plus 1, and g of x equal to the square root of x squared plus 2. Let us calculate f of g of x. What is the composite of f with g? F composed with g of x is f of g of x. Right? So that means f of the square root of x squared plus 2. And how does that, what do we have to do? What does f do? F takes takes the input, it multiplies it by 2, and it adds 1, right? So that's what we have to do. We have to take the input, which in this case is the square root of x squared plus 2. We multiply it by 2, and then we add 1. And there you go. That's the composite. How many people can't follow what I just did? Okay. So at least one person needs me to do it in a different notation. Now, there's different ways we could do this, all right? But a notation I was thinking about, which might be kind of a nice way to do it, would be like this. How about this? F composed with g of x. We could think about like f of g. We could think about it like f of g, right? So what we do is we put x equal to g for the formula in f, right? What's the formula for f? 2x plus 1, right? So f of g would be 2g plus 1, right? But then what is g equal to? Well, g is equal to the square root of x squared plus 2, right? So we could put that as 2 times the square root of x squared plus 2 plus 1. So we could, maybe that's a better way to do this. Is that better? Does that make more sense to everybody? A lot of times people will invent another letter. They'll say let u equal to g of x, and they'll like look at f of u and substitute it in. But I figure we could just as well use g if we're going to do that. Now technically, that's an abusive notation because g is the function, whereas g of x is the value. But I don't think I should belabor that point. I don't think that's going to help you. Let's do g composed with f. What would the difference be? I'll do it in red. What would g composed with f be here? So you're giving me the answer, which is great, but let me just take a step back. Let me use that same kind of, what I did in the blue I might call training wheels, you know, but maybe we should keep the training wheels on here for a little bit, right? What would g of f be? Well, you're giving me the answer, which is good, but what I'm fishing for is to just take f and put it in the place of x, right? So what? F squared plus 2, and then we'll get to what you were telling me just a second ago, which was what? Oh, and I was supposed to put plus 2 here, right? Yeah, sorry about that. And there you go, yes. Are these equal? Look at this. Is g composed with f equal to f composed with g? No, they're not, right? They're not, no. Look at this formula. Look at that formula. Are these equal? Yes, they're not equal. There's no algebraic simplification of this. If you're thinking that this can be simplified to like 2x plus 1 plus the square root of 2, no. This cannot happen. Like the square root of a sum is not the sum of the square roots. Like there's no. What I'm trying to say is if we have the pattern like Pac-Man squared plus Ghost squared, it is not equal to the square root of Pac-Man squared plus the square root of Ghost squared. Like that is not what happens. That is not I mean, let's see here. For example, if you had the square root of, like 3 squared plus 4 squared, this would be, right. Is that equal to 3 plus 4? Well, this is the square root of 9 plus 16, which is 25. Right? And the square root of 25, well, that's 5. Is 5 equal to 7? I mean, it's not, right? I mean, we can't make this simplification. We cannot break square roots over sums. It's just, I mean, I wish it were that. Wish it worked that way, but it does not. So, but yeah, these are not the same formulas. Generally speaking, f composed with g and g composed with f are different functions. Usually they're different functions. I mean, you could look at some pathological cases where they'd be the same, but typically they're different. Now, what about the product? What would f of x times g of x here be, by the way, guys? is what? It's 2x plus 1 times the square root of x squared plus 2. And that is, by the way, also equal to the square root of x squared plus 2 times 2x plus 1, because we can commute the multiplication of real number quantities, right? Real numbers commute, their multiplication commutes. And this right here is gf of x, whereas the other side is fg of x. In other words, fg is equal to gf. Since the equation above holds for like all x in the domain, it follows that the function f times g is the same as the function g times f. Like f times g is g times f. It doesn't matter which you multiply first or second. In contrast, when we compose functions, really quite different. Which one comes first, which one comes last, it matters. Just like it matters whether you put your shoes on first or your socks on first. That's like putting shoes and then socks on. Excuse me, socks and then shoes on. That's an example of composition. What's that? You thought what? It doesn't exactly. In multiplication, it doesn't matter. Like, because we get the same formula, whether we multiply this times that or that times this. I mean, either way, it's the same. That's all I'm saying. So, guys, let's look at some more examples of composition. Can I erase the burgundy? What's it with you guys and sleep today? Like, they were telling me that they wanted to go to sleep before you got here. It's like some kind of group chat in this class. Let's go tell Dr. Cook it's time to go to sleep today. It's going to be it's a change in the weather. I can see that. That's a valid point. The weather is lovely today, is it not? No? I'm loving this weather. Time stands still. 128 for 3 minutes, okay. 128. Oh, yeah. Oh, my goodness. Oh. Example. Suppose we had f of x equals to 3x plus 1 and g of x equal to 2x, just like that. We can calculate f composed of g of x. What do we get? So I'm going to think of it as f of g, that's 3 times g plus 1, which is 3 times 2x plus 1 in our current context. So we get 6x plus 1. By the way, this is an example of a kind of neat pattern. Both of these are what? These are linear functions, right? What's the slope of the first one? 3, and the slope of the inside function's 2. And check it out. This is also a linear function. So the composite of linear functions is again a linear function. And it looks like the slope of the composite is just a product of the slopes. So that's kind of neat. This actually turns out to be the reason that we get a chain rule in calculus later. So I just mentioned it in passing here. All right, let's look at an example. We've got some fractions in it. F of x is 1 over 2x plus 3, and g of x, we'll keep it relatively simple, square root of x. All right. So f composed with g of x, what's that equal to? We do f of g, right? Which is 1 over 2g plus 3. So what's the formula for f of g of x? It is 1 over 2 times the square root of x plus 3. What would happen if we calculate g composed with f? Yeah, we get square root of f, right? Which is square root of what? There you go. Right. All right, now you need to go work out about 20 of these for yourself. This is what you need to do next. About 20. Until you're bored with it. You're like, we're already bored with it. Okay, let me choose my words more differently. Work enough of these that you genuinely understand it from your heart. Yes. What's that? The best thing we've done. That was not, there's no sarcasm there. Okay. Usually. So I just heard that you guys were satisfied with what we're doing, therefore I will do something else. Definition, a function f, is 1 to 1, or sometimes people will call it injective, if f of a equal to f of b implies a equals to b. Now, if you look at a graph, right, and the graph looks like this. If you think about, say, this point and this point, if that's my A and that's my B, if your graph looks like this, right, and you drew a horizontal line through the graph, what would the horizontal line would intersect the graph at 2 points, right? See that? So we have f of A equal to f of B, yet A is not equal to B. So f is not 1 to 1. It's not 1 to 1. Two distinct inputs can create the same output. If that's the case, the function's not 1 to 1. And we also say that the function does not pass the horizontal line test. So a way to check if a function's 1 to 1 is to check that each horizontal line you can draw through the graph just passes through one point in the graph. So like a different example, if you had something that was just like this, then this graph passes the horizontal line test, because if you think about like horizontal lines through it, right? Each horizontal line cuts through the graph just once. So this, if I was to call this, say, y equals to g of x, then this function g would be injective. It would be a 1-to-1 function. All right? So you're like, well, that's great. Why are we talking about this? Well, we would like to talk about inverse functions. And basically the theorem is this. We can define an inverse function for a graph on some domain, provided that the function is 1-to-1 on that domain. So if the